talk about some of the cosmological aspects, and then the third lecture about connections to cosmic rays and neutrinos. So, basic models. First, of course, there were the basic observations. The first GRB detections, GRB stands for gamma ray bursts, were done by accident. They were these military US. My mic is not on? I'm sorry. All right. They were obtained by accident scientifically. The Vela satellites were monitoring for nuclear explosions, and they, this was one of those examples where you develop a technology for one purpose, but you achieve a significant result in a completely different area. So in this case, what they discovered is these flash of gamma ray bursts, and unlike nuclear explosions, these were satellites that were looking at the Earth, but these flashes of gamma rays came from the opposite direction, away from the Earth. And so after ruling out that it was some extraterrestrial people making signals, it was decided that it was an astrophysical event. And the first discovery was in 1967, but being classified, it wasn't published until 1973. And after that, a number of other observations were made. Then the Soviet military satellites also looked at them, and other civilian satellites like the SNM, and the Ginga satellites from Japan, etc. And the thing is that these were flashes, but only of gamma rays. So it was very rare at that time to see something which is astrophysical, but it's only seen in gamma rays, not in radio, not in optical, not in X-ray, it was gamma rays. So that was rather puzzling. And the other thing that was bad was that, of course, gamma ray detectors don't have a good angular resolution. So it was possible to determine that more or less they come from, 5 or 10 degrees in that direction, but you couldn't really pinpoint it to a galaxy or to a star or anything, because the gamma ray detectors are not good at imaging. So for 25 years, they were not seen at any other wavelength except gamma rays. So why gamma rays only? Why only brief flashes of tens of seconds? And essentially, what are they? Are they near, are they far, etc.? So these gave rise to a lot of highly speculative theoretical models, which were all completely incompatible with each other. And much progress wasn't made until the launch of the Compton Gamma Ray Observatory, which was a dedicated mission for gamma ray astrophysics deployed by the Space Shuttle in 1991. It had a complement of 4 instruments. A low-energy instrument called BATSE, which had 8 detectors, so looking in all directions, in the 10 keV to 20 MeV range. And then OSSI and COMTEL, they were high-energy detectors, and EGRET was in the GeV range. So in more detail, here are some of the statistics. It was launched in 1991, was in operation for about 9 years. So the total range was from 30 keV to 30 GeV. And it had a number of very interesting results. So one of them was that it discovered that the gamma ray burst events are distributed isotropically over the sky. They come from everywhere, more or less uniformly distributed in space. And if something is completely isotropic, then you decide that it has to be either very local, it's smaller than the size of our galaxy, or it's extremely large. It's cosmological distribution, like the galaxies, they're distributed isotropically. It also found that the time durations come in 2 groups, long bursts or short bursts. And the spectra, the gamma ray spectra are non-thermal. It's not a black body function, it's not a Planck function, it's actually a power law, in fact a broken power law. And the gamma rays actually vary in time, so there is a time variability. Now when a gamma ray burst comes off, it actually outshines even the sun in gamma rays. It completely, if you had gamma ray eyes, it would completely blind you. So the distribution, as I was saying, is isotropic. You can see that there is in a galactic map, there is no way of telling that there is any agglomeration towards any direction. And so if you consider that the Earth is somewhere here in the galaxy, it is the center of the galaxy, okay, then either the distribution is so small that it sort of doesn't recognize that there is a galactic plane, or it's so large that it ignores the presence of the galaxy. So what you expect then is that the flux is the luminosity divided by 4 pi the distance squared, actually, you use the luminosity distance. And so the number of objects with flux greater than phi is expected to go proportional to flux to the minus 3/2, right? Because the flux goes as r squared and the number goes as r cubed. So you expect a Euclidean minus 3/2 slope. And more or less this is what is observed, except that here there is, at very low fluxes, there starts to be a deficit. And so the deficit can be interpreted as being due to the fact that you have a cosmological distribution, but at very low fluxes, the cosmological redshift, the expansion of the universe, causes the flux to start becoming more and more dim. So these really suggested that this was a cosmological distribution, objects which are at cosmological distance, like the distant galaxies. The light curves can be very time variable and very messy, durations of tens of seconds. There is a great variety of them. Some of them are highly variable, some of them are smoother, and some of them have a very short duration, a very, very spiky duration. Some have variability as short as 200 milliseconds. So it's very difficult to imagine what object at cosmological distance can produce pulses of gamma rays that short. You need a large object, obviously, to be visible out at cosmological distances, a lot of energy. And but then, from causality, that implies a very small size. These just is a plot of the durations. Now, it's a histogram of how many bursts of short duration, how many of large duration. So that is so-called short bursts, less than 2 seconds, and long bursts longer than 2 seconds, and extending it to 1,000 seconds or so. So there appear to be 2 different classes of gamma ray bursts, which are well divided by their duration. As it happens, the spectrum is also harder for the short bursts. So if you consider the short, if you consider the short duration bursts and you take the ratio of so the BAT instrument had 4 bands, low energy band, medium energy band, somewhat large, high energy band, and very high energy band. The ratio of the 3 to 2 band gives you an idea of a hardness ratio. The short bursts have a harder spectrum on average than the long bursts. So not only are they short duration, but they also have a somewhat harder spectrum. And so there is another plot of the same thing. The short ones have a harder spectrum. And this shows the type of spectra. So if you try to parameterize it, it's usually a broken power law. Not exactly power law, but you can approximate it by a broken power law. And there is a phenomenological function called the band function, which can parameterize it. And the parameters of the low energy slope and the high energy slope and the break energy, they all have a distribution. So the break energy is usually in the MeV range, half MeV to 1 MeV, and the low energy slopes for photon number are roughly -1, and the high energy slope is roughly -2, -2.5. There was also GeV emission at GeV energies detected by the IGRIT detector on CGRO. This was one particular burst, and you can see that it was this was the MEV emission, and this was the GeV emission. The GeV emission starts more or less at the same time as the MEV, and then it lasts for a long time. The satellite orbits the Earth, so there is an Earth occultation period, which is something like over an hour, hour and a half. And even after the Earth occultation was over, the emission at GeV energies continued. So several hours worth of duration at GeV energies, whereas the MEV emission is only tens of seconds. So the GeV emissions seem to last much longer. How to interpret all these? Of course, as I mentioned, initially there were hundreds of models, but as Compton the Compton Observatory started producing all these observations, then the models finally settled down into a more or less coherent picture. So first of all, some numbers. The rate of burst is more or less 1 per day out to cosmological distance inside a Hubble radius. They are detected out to almost the largest distances, redshifts of 9.3, that you detect objects. Quasars, the most distant quasars, the most distant galaxies, are more or less at these kind of frames. So you detect these objects out to that distance. And the fluence, flux times multiplied by time, is roughly 1 photon per square centimeters in gamma rays. But that's a lot of gamma rays. Of course, you need a detector with more than 1 square centimeter, but typically it's maybe a square meter or whatever that they're detecting. And if you consider what is the energy output is very large. It's a good fraction of 10% maybe of a solar rest mass. So 10 to the 53 Earth is a very large amount of energy. But if the energy is injected in a collimated fashion, then the energy flux would be lower. It's interesting to compare it to other objects. So the total gamma ray energy put out by a gamma ray burst is the same energy that the sun puts out in 10 to the 10 years. So 10 to the 10 years is more or less the age of the universe. So a burst puts out in tens of seconds as much energy as our sun puts out over the entire history of the sun, or as much energy as the galaxy puts out in 1 year. So it's a lot of very concentrated energy. Now, what has finally come to, the model that has finally emerged is that this has to be some kind of a cataclysmic stellar phenomenon. And the kind of phenomena that can produce these are of two types. One of them is that you can have two very compact objects like a neutron star binary or a neutron star black hole binary, both of them more or less of 1 solar mass. And these objects are observed to exist, double neutron star binaries, and it's known that they will merge due to gravitational wave radiation, the orbit shrinks, and then they will collapse to a central black hole, which will accrete the debris matter, and then simulations show that the relativistic jet will form. And the duration of that, more or less, is what you expect for the short bursts done for these brief merger events. The other paradigm is that of the collapse of a massive star, where the core collapses because it has exhausted the nuclear fuel, and the core loses pressure, it collapses into a black hole, and the matter around it is being accreted, so you get again an accretion episode into a central black hole, the production of a jet. But these are longer lasting. It's a large star, so the matter falls in for a longer time. And you expect then that to last for, tens of seconds. Now, what happens when you have these initial collapse? You have a lot of matter falling into a very small region, and it's a large amount of energy, which you presume that the size of the emission region, the black hole region, is maybe 10 or 100 kilometers. So from causality, from the variability time scale, that's what you expect. And so it's going to produce a fireball, a very hot ball of radiation, protons, electrons, and positrons, which is going to have a very small optical depth to gamma-gamma interactions. So it's going to be a fireball that expands. It's like a giant nuclear explosion, except it's much more energetic. And eventually that's going to produce the gamma rays. So it's one thinks that these will produce an expanding fireball. And the question is, how fast does it expand? Now, one observes more photons of energies in excess of 10 GeV. In fact, up to 100 GeV has been observed. And you know that photon-photon interactions will produce electron-positron pairs, and the threshold is half an MeV, yet you have observed 10 or 100 GeV photons. How can you explain that? The way you can explain it is if the fireball is expanding so fast that the photons can interact only at shallow angles. And so if they interact at shallow angles, then you can, so that the causality angle is 1 over the Lorentz factor, and from that you can infer that the Lorentz factors of the expansion are of the order of hundreds. So these fireball must expand at very relativistic velocities. Lorentz factors of the order of 100 or 500 or 1,000. It's not very large by LHC standards, but it's very large for relativistic hydrodynamic standards. These bulk acceleration. It's not a single particle, but it's a fluid accelerating at these very large Lorentz factors. So you can set up the equations of relativistic hydrodynamics. You look up Landau-Lifshitz fluids, chapter 14, relativistic hydrodynamics, and you set up the energy impulse tensor, and you consider the force velocity and the relativistic enthalpy, and you can set up the equations of particle number conservation, momentum conservation, and energy conservation. And you can make some approximations, consider that during a certain amount of time it's a steady state, and you figure out that during the expansion, the particle density will decrease proportional to 1 over r squared gamma, while the Lorentz factor will increase initially proportional to radius. That's because you're converting internal energy into bulk kinetic energy. Okay, so as the fluid cools in its own rest frame, that energy is going into bulk kinetic energy. It accelerates in the same measure that it cools. So initially the bulk Lorentz factor will grow radially, and then when it becomes non-relativistic in its own rest frame, the gas, then it will drift at a constant velocity. And one thing that you expect is that eventually shocks will develop in these expanding fluid. First, because you may have portions of the flow that are faster, which catch up with slower portions, and those will undergo a shock at some intermediate distance. And then eventually, as the fluid expands, it will interact with the external interstellar medium and start to decelerate because it's hooking up more and more external matter. And then the bulk Lorentz factor starts to decrease as a power law, inverse power law. So the fireball shock model then is that you have, let's say, a core collapse, or maybe a binary neutron star merger, a relativistic jet is produced. Internal shocks occur where faster shells of matter collide with slower shells, And then you'll have particle acceleration. When you have shocks, you have Fermi acceleration, particles bouncing across, back and forth across the shock. They interact with the magnetic field, synchrotron radiation. So there you can produce the gamma ray prompt emission of the gamma ray burst. And then the jet continues to travel until it starts being decelerated by the external medium, and then as it slows down, the synchrotron radiation, it gets less and less Doppler boosted, and so it gets longer and longer wavelength. It goes from gamma rays to X-rays, to optical to radio, and your timescales get longer and longer, so you expect a long-lasting afterglow. So the shocks, the internal shocks, you can calculate roughly where they will occur. If the shells differ, if the Lorentz factor of successive shells of ejected matter differ by order of magnitude, roughly of changes of order 2, the shocks will occur at radii of about 10 to the 12 centimeters if the variability timescale is 10 to the minus 3 seconds, and the bulk Lorentz factors are of the order of 100. The external shocks occur after you have swept up a large enough amount of matter that the bulk kinetic energy of the swept up matter being pushed ahead is comparable to the initial total energy of the burst. That condition, so the external shock radius is of the order of 10 to the 16, 10 to the 17 centimeters. The radius of the central black hole is 10 to the 6, 10 to the 7 centimeters, so these, many orders of magnitude above where the central engine is. So in the internal shocks, you have two shells that collide with each other, and then you get a shock moving forward, a shock moving backwards, but the center of mass is moving forward with the flow. And in the external shock, you have here the quiescent static interstellar medium, a fast medium, very relativistic medium coming in, and then you have a contact discontinuity, and you have a forward glass wave, which is very relativistic, and the reverse shock, which is moving into the ejecta. Of course, the contact discontinuity is moving more or less at the same velocity as the ejecta, very relativistic. The reverse shock is only semi-relativistic relative to the fluid. Numerical simulations have been made of such a jet propagating inside a progenitor star, and as it breaks out, so you can actually get a fair amount of detail about how these jets propagate through the star, and the fact that they can achieve these high Lorentz factors. The radiation, the characteristics of the radiation, so there are these two regions, the internal shock region, the external shock region. There is another radius, which is the radius where the fireball becomes so-called optically thin, where the mean free path of the photons becomes comparable to the size of the region, so from here on the photons can escape freely. You might get photons escaping from there, but the non-relativistic photons are thought to be, the non-thermal photons are thought to be produced in the internal shock or in the external shock. So the synchrotron radiation is a non-thermal process. The electrons accelerated will be a power law, relativistic power law. So in this case you get a broken power law of photons, which can be in the NeV range. And then you can have, in the external shock, you can have synchrotron radiation, but also these synchrotron photons can be scattered, upscattered by relativistic electrons here. And then you get a higher energy inverse Compton spectrum. So you expect in a unit of frequency times flux per unit frequency, these would be energy squared times number of photons per energy. The internal shocks might be something like that, or if there is an inverse Compton component and a double broken power law, which that would give you the GeV radiation. The external shock also has a reverse shock component, I told you, and that typically radiates in the optical. So you can have also the reverse shock producing an optical radiation, while the forward shock is producing high energy radiation. So the other thing is that these synchrotron inverse Compton spectrum, which first occurs when the fireball starts to decelerate, as the fireball gets slower and slower, its advance gets slower and slower because it's sweeping up more and more matter, which holds it back more and more. Then the Doppler boost of the radiation gets less and less, so the peak of the radiation moves towards lower energies in time. You start out with X-ray and gamma rays, then it becomes optical, then it becomes radio. So you expect these afterglow of the gamma ray burst to be at lower energies. Now, I mentioned to you that Compton Gamma Ray Observatory only observed gamma rays. It hadn't observed any of these X-ray, optical, and radio. So these predictions were made before the observations, actually. And so these was something that was expected but wasn't discovered until later. So the shortcomings of Compton Gamma Ray Observatory was that it didn't have a good imaging detector because in gamma rays it's hard to do that. So its position accuracy was very poor. And so it was useless to try to point quickly an optical telescope in some direction because you have to search such a large area that by the time you finish your search, the gamma ray burst had long ago faded. So a new satellite was launched, an Italian-Dutch satellite, a European satellite called Bepo-SAX. And these had the capability of, so it had a wide field of view gamma ray detector, and then it had the capability of slewing in 8 hours. It was, it could get a rough direction, and then it could repoint, it could repoint, that is the satellite, in about 8 hours to focus a much better resolution X-ray detector, for which there is optics. You can get a much better resolution. So these was finally able to detect the X-ray afterglow of one burst. So in these bursts, 970228, that's the year 1997, February 28, that's how the numbers are. And you can see an initial X-ray that sort of fades in time. So 2 days later, February 28, March 3, it has faded. And the way it fades in a nice power law. So in the X-rays, it fades like that. In the optical, it fades like that. So you detected the X-ray, then later with optical telescopes, you detected the optical. The optical also fades as a power law. And this was actually, this kind of power law fading had been predicted. This was what expected from such an expanding power law. And the spectrum that you expect from a synchrotron spectrum of the afterglow is, a broken power law, as I mentioned. These is the so-called band function. Synchrotrons radiate from power law, electrons radiate with a power law. This is the minimum Lorentz factor of the electrons, and the maximum somewhere here. You expect a break here when the electron cooling time is shorter than the dynamic time of the expansion. And then here you expect the self-absorption break. So observations actually have confirmed, the data points fall on these. So the theory of these